Beyond the edge of the universe, there is no giant wall, no final border, and no simple end to space. What looks like an edge may only be the limit of what light has had time to reach us. In this video, the journey moves beyond distant galaxies, beyond the oldest light in the cosmos, and into the deeper question of what science really means when it talks about the edge of reality. If this kind of calm space documentary helps with sleep, focus, or curiosity, please like the video, subscribe to the channel, and let the journey begin. From the widest outward view, the universe seems to offer an edge because sight itself always ends somewhere. In the night sky, vision meets darkness long before thought accepts that space may continue far beyond what any eye can hold. Stars appear as scattered points, galaxies as faint veils when instruments deepen the view, and between them lies a blackness that feels complete. This feeling is ancient and natural. Human perception is trained by ordinary landscapes, where every horizon belongs to a surface, a boundary, or a distant obstruction. Land meets sky, sea meets air, clouds close a scene. In daily life, an edge usually means that something truly ends there. When the same instinct rises under the stars, it searches for a final border in the heavens as well. It expects a rim, a wall, a last surface where the universe gives way to something else. But the sky does not present such a thing. It presents only the gradual failure of light. This first outer region of the subject is therefore not a place in space, but an appearance in observation. The apparent edge of the universe is the point where the visible scene thins into absence. It is not marked by a line. It is not drawn as a circle of fire or a shell of stone. It does not shine with a special colour to announce that everything beyond it ceases. Instead, the view fades by degrees. Bright nearby stars give way to fainter stars. Faint stars give way to dim patches of more distant systems. Deeper observations reveal more structure, more galaxies, more weak light arriving from remote times. Yet even the most sensitive view still reaches a frontier where no more detail is presently seen. That frontier feels like an edge because every act of seeing has a limit, and the mind often treats the limit of seeing as the limit of reality. On Earth, darkness usually means either that light has not arrived or that an object blocks it. In the wider universe, darkness often means something more subtle. It can mean that light is too weak, too stretched, too distant, or simply not yet accessible to a given method of observation. The black background of the night sky is therefore not empty in the ordinary sense. It is a field in which visible signals are sparse, distant, and unevenly distributed. The eye fills that sparseness with silence. A telescope reduces some of the silence by gathering more light, but it does not remove it entirely. Each improvement reveals that what seemed blank contains hidden structure. This pattern repeats across the history of astronomy. A dark patch becomes a star field. A faint blur becomes a galaxy. A single source becomes many sources. The supposed edge retreats, not because the universe shifts outward, but because observation grows deeper. Even so, the impression of an outer boundary remains powerful. It remains powerful because the sky is not merely measured, it is experienced. A clear night carries a dome-like appearance, and that appearance encourages enclosure. The stars seem set upon a vast surface overhead. Their distances do not announce themselves directly. Brightness can mislead. Faintness can mislead as well. The human senses do not naturally distinguish between something truly near and something enormously far but luminous, or between something absent and something present but beyond easy detection. The apparent edge of the universe begins in that limitation. It belongs to the way a finite observer receives an immense reality. The sky does not reveal all at once what is there. It offers only what reaches the instruments of sight, and it does so with severe restraint. This restraint creates one of the calmest and deepest tensions in cosmology. The universe appears open, but vision is closed. Space does not seem to present a physical barrier, yet observation still stops. This stopping point gives rise to the language of edges, ends, and beyond. Such language is understandable, but it can mislead when it turns a visual frontier into a material border. The night sky contains no visible evidence of a cosmic cliff. There is no place where galaxies appear to pile against a final wall. There is no seam where the fabric of space is seen to end. There is only a thinning record of light, arriving across greater remoteness, until present methods reach what they can no longer cleanly recover. The apparent edge is real as an observational experience. It is not established as a built structure in the universe itself. The deepest astronomical images make this especially clear. When observation remains shallow, the sky contains scattered stars and broad darkness between them. When observation becomes more patient, the darkness fills with remote galaxies, so numerous that the black intervals begin to look less like empty reaches and more like places where light still lies below immediate notice. The scene grows crowded without ever becoming full. There is always more black around the points of light than the mind expects. This contrast can feel unsettling. The visible universe presents itself not as a packed surface, but as a sparse, luminous record laid across darkness. That record has depth, and depth makes the idea of an edge difficult. A flat wall would close the scene. The real sky keeps opening while still refusing complete disclosure. So the first sense of the universe ending does not come from finding a final object. It comes from reaching the end of what vision presently gathers. This difference matters. A final object would be part of the universe as a thing. A limit of observation belongs first to the meeting between the universe and the act of seeing it. In that meeting, the sky behaves with great quietness. It does not declare where reality stops. It only withholds more light than it gives. The result is a dark frontier that invites imagination but resists certainty. From the widest outward view, the edge of the universe appears as a visual horizon made of fading light, sparse structure, and the disciplined silence of distance. It is not a cosmic shoreline. It is the outer face of what the visible sky is willing to reveal at all. The universe appears larger than any complete map because observation always begins within a limited field of arrival. What can be seen from Earth, or from any instrument near Earth, is not the whole of existence in any confirmed sense. It is the portion from which light, or other signals moving at the speed of light, has had enough time to reach the present moment. This visible portion is called the observable universe. The term sounds broad, but it is careful in meaning. It does not claim to describe all that exists. It describes only the region that can, in principle, be observed from a given place because signals from that region have completed their journey. The apparent edge of the universe, in this second and more precise sense, is therefore not a wall in space. It is the boundary of what has become visible through time. This idea depends on a simple but very powerful fact. Light does not cross the cosmos all at once. It travels, and because it travels at a finite speed, every act of seeing is also an act of receiving something late. On Earth, the delay is too small to notice in everyday life. In astronomy, delay becomes the basic condition of all sight. The moon is seen as it was a little more than 1 second ago. The sun is seen as it was minutes ago. The nearest stars are seen as they were years ago. Distant galaxies are seen as they were millions or billions of years ago. This means that looking deeper into space also means looking farther back in time. The observable universe is built from this union of distance and delay. It is the full range from which signals have had time to arrive since the universe becomes transparent enough for light to travel freely across space. The phrase observable universe can sound as though the universe has been divided into two clean parts, one visible and one absent. But the true picture is calmer and more exact. The observable region is not marked by a painted shell or a final ring of matter. It is a horizon. A horizon is a limit in what can be reached or seen from a given position. On Earth, a horizon can arise because a curved surface hides what lies farther on. In cosmology, the horizon arises because the universe has a finite age and light has a finite speed. These two facts work together. If the cosmos has not existed forever in its present expanding form, then light from the most remote places has had only a limited amount of time to travel. Some signals have reached Earth, others have not. The horizon separates those two conditions. Within that horizon lies an enormous realm. It contains galaxies in numbers beyond ordinary mental grasp. Great filaments of matter, vast darker gaps between clusters, and radiation that has crossed nearly the whole visible depth of cosmic history. Yet even this immense region is still a portion rather than a totality. The word observable carries that discipline inside it. It reminds the mind not to confuse the widest thing currently seen with the widest thing that exists. The horizon can define what is accessible without defining what is ultimate. This distinction is one of the central acts of restraint in cosmology. Science describes the visible domain with increasing precision, but it does not simply declare that nothing exists beyond the reach of present observation. The observable universe also changes in a subtle way with time. As time passes, light from more distant regions has longer to travel. In that sense, the visible domain can grow, because signals that once remain beyond reach may later arrive. At the same time, cosmic expansion alters the paths and distances involved, making the full story more intricate than a simple sphere spreading outward through stillness. Even so, the basic principle remains steady. What can be observed is controlled by the history of the cosmos and the travel time of light. The edge in this context is not the edge of space itself. It is the present limit of successful contact through radiation. This helps explain why the observable universe feels both complete and incomplete at once. It is complete in the practical sense that every cosmic image, every distant galaxy, every measurement of deep space, and every ancient signal belongs within it. All astronomy works inside this realm because all received information must come from somewhere that has had time to communicate with Earth. Yet it is incomplete in a larger philosophical sense because the method itself leaves open the possibility of more beyond. Observation provides a horizon, not a final closure. The darkness beyond present reach is not automatically a proof of absence. It is first a sign that no signal from there has arrived here. The idea can feel unsettling because it separates reality from accessibility. Human habits of thought often treat the knowable and the real as nearly the same, at least in practical life. Cosmology loosens that bond. It shows a universe in which the visible domain may be vast almost beyond language, and still not include the whole. The observable universe is therefore not a small enclosure. It is an immense sphere of received history. Every direction leads toward a farthest region whose light is only now arriving, or has only recently become available to measurement. That farthest region marks the current visual limit, but the limit belongs to connection, not necessarily to existence. So the apparent edge of the universe becomes more exact in this second region of understanding. It is the edge of the observable universe, the boundary set by finite cosmic age and finite signal speed. It is created not by a material barrier, but by the simple fact that light must travel and that time has not been unlimited. Beyond this horizon, science becomes cautious. Within it, the cosmos already contains more depth, more age, and more structure than ordinary intuition can comfortably hold. The observable universe stands as the true first answer to the language of edges. What lies at the farthest visible distance is not a wall, not an ending, and not a final surface. It is the present horizon of light itself, the outer limit of what has had time to be seen. The observable universe seems to place Earth at the centre, but this impression belongs to perspective rather than privilege. Any observer, in any galaxy, at any location that can support measurement, would describe a similar horizon gathered around that observer's own position. This is one of the quiet but difficult ideas in cosmology. The visible universe appears arranged around the one who sees it, yet this does not mean that the universe itself is built around that place. It means only that observation begins locally and spreads outward through arriving light. The horizon of visibility forms a sphere around the observer because signals come inward from all directions toward that observer. The pattern is natural, but the mind easily mistakes it for evidence of a favoured location. This mistake is understandable because ordinary life trains thought towards centres. A city has a centre, a room has a centre, a circle drawn on paper has a centre. Human experience is full of structures whose form is organised around a middle point, and once the observable universe is pictured as a great sphere, instinct begins searching for the one true middle of all things. Yet the observable sphere is not like a solid object suspended in a larger room. It is not a globe with a marked core. It is a region defined by what has had time to send signals to a given place. Change the place, and the sphere changes with it. The observer does not stand at the centre because nature has crowned that location. The observer stands at the centre because every observation starts where the observer is. This idea becomes clearer when the local sky is compared with a more familiar horizon on Earth. A person standing on open ground sees the horizon arranged around that standing place. Walk several kilometres, and the horizon shifts. The circle of visibility is still centred on the new position. No special place on the surface has been revealed by the earlier view. The horizon follows the observer because it is created by the relationship between the observer and the limits of sight. The cosmological horizon is not identical to an earthly one, but the comparison helps. It shows why a horizon can surround a viewer without proving that the whole world is built around that viewer. In the same quiet way, the observable universe surrounds Earth without granting Earth any special rank in the total structure of the cosmos. Modern cosmology rests on this absence of privilege. At the largest scales that can be measured, the universe appears broadly similar in all directions and from all ordinary locations. Once smaller local irregularities are averaged out, galaxies gather into clusters, filaments, and great empty regions. So the nearby universe is not smooth in every small detail. But over vast enough distances, no strong evidence shows that one broad region is the unique centre from which everything else spreads in a simple outward shell. The expansion of the universe does not behave like debris rushing away from a single explosion point into pre-existing emptiness. Instead, the large-scale pattern is more subtle. Space itself expands, and this expansion can make every distant galaxy appear to recede from every other distant galaxy when viewed on very large scales. In such a picture, There is no need for a central platform from which the whole process begins to look correct. This is why the phrase center of the universe usually misleads more than it helps. There are many local centers in astronomy. A planet has a center, a star has a center, a galaxy has a center, a galaxy cluster can have a central region as well. But the universe as a whole, in the standard cosmological description, is not known to possess a single spatial center in the everyday sense. The visible sphere around Earth is a horizon of access, not a cosmic throne. It marks how far observation reaches from here. It does not identify the middle of all existence. The same is true of edges. If there is no special center established by observation, then the apparent edge of the observable universe cannot be treated as the rim of a single giant sphere sitting within a larger emptiness. It is the limit of what is visible from a location, and every suitably placed observer would trace a similar limit around a different location. The far boundary is therefore personal in viewpoint, but not personal in importance. It belongs to perspective, not to status. This distinction removes much of the old image of the universe as a bounded chamber with humanity somewhere near the middle. The modern picture is less intimate and more even. It gives every observer a centered view without giving any observer central importance. This can feel almost paradoxical at first. Every observer can be at the center of an observable universe without requiring many absolute centers to exist at once. The answer lies in the meaning of the word observable. Each observer defines a different visible domain, because light reaches different places along different paths and at different times. These domains overlap enormously if the observers are not too far apart, but they are not identical in every detail. The center in each case is not a universal landmark fixed in space. It is simply the location at which observations are made. Once that is understood, the paradox softens. Many centered views do not imply many absolute centers. They imply that visibility is always organized around the act of looking. So this region of the subject removes one of the most persistent false edges in cosmology. The universe does not present Earth as its middle, and the observable horizon does not turn the visible cosmos into a walled sphere with one privileged core. The apparent centrality of the observer arises naturally from how light arrives and how horizons are defined. Every observer receives a universe gathered around that observer, but the gathering is optical and historical, not hierarchical. The result is quieter than older visions of the cosmos and, in its own way, more unsettling. The universe can surround the observer completely while refusing to place that observer at the center of reality itself. The apparent edge of the observable universe takes on a new meaning once space is understood as expanding. Distant galaxies do not simply sit in a fixed cosmic chamber, while their light crosses an unchanging emptiness. The larger structure between galaxies changes while the light is on its way. Space stretches, and as it stretches, the light traveling through it stretches as well. This effect is called cosmological redshift. The word redshift refers to a shift of light toward longer wavelengths, which means the light is drawn toward the redder part of the spectrum. In simple terms, the waves become longer while they travel across an expanding universe. What reaches a telescope is therefore not exactly the same pattern of light that leaves a distant galaxy. It arrives altered by the history of the space it has crossed. NASA and ESA both describe cosmological redshift in this way as the stretching of light by the expansion of the universe, with more distant light generally showing greater stretching. This change is one of the central reasons the universe appears to have a receding edge rather than a fixed outer wall. As galaxies lie farther away on the larger scales, the expansion between them becomes more important, and the light they send arrives more stretched and more dimly distributed across wavelength. The farther the source, the more time its light spends crossing expanding space, and the more strongly the expansion leaves its mark on that light. A distant galaxy is therefore not only far away in the ordinary sense of separation, it is also seen through a record of cosmic change written directly into its radiation. This is why redshift becomes a measure of depth. Astronomers compare known features in a spectrum, such as familiar absorption or emission patterns, with where those features appear when the light reaches Earth. If the pattern is shifted toward longer wavelengths, the amount of the shift helps indicate how much the universe expands during the light's journey. That is why modern surveys use redshift to connect distance with the large-scale history of expansion. The effect is often described through motion, and that language is useful so long as it remains careful. Distant galaxies do appear to recede from one another on large scales, and this recession correlates with distance, a pattern first recognized in early measurements of galactic spectra and still central to cosmology today. Yet the deepest meaning is not that all galaxies simply rush through space like fragments from a blast moving across a pre-existing void. The more accurate picture is gentler and stranger. Space itself expands, carrying greater separation into the large-scale fabric of the cosmos. In that setting, redshift is not merely the ordinary color change caused by an object moving through still surroundings. It is a sign that the surroundings themselves evolve while the light travels. NASA and Hubble educational material describe this as galaxies moving farther apart as the universe expands and their light elongating into redder wavelengths. This does not mean every part of the universe expands in the same way at every scale. Bound systems resist the general stretching. A galaxy does not swell merely because the universe expands. A solar system does not drift apart under ordinary cosmic expansion. Gravity and other local forces hold such structures together strongly enough that the large-scale growth of space does not simply pull them open. NASA educational material notes that nearby gravitationally bound objects do not display cosmological redshift in the same way distant large-scale structures do. This distinction matters because it keeps expansion in its proper domain. Cosmological redshift belongs above all to the deep universe, where vast separations between clusters and galaxies are measured across enormous spans. It is a property of the large fabric, not a universal loosening of every smaller structure. Once this is understood, the edge of visibility becomes less like a border and more like a gradient of altered light. The most distant objects are not merely dim because they are far away. Their light also arrives displaced from the wavelengths in which it is first emitted. Radiation that begins as visible or ultraviolet light in the early universe can arrive today in the infrared, because cosmic expansion stretches it along the way. NASA explains that this is why infrared telescopes are essential for studying the first remote galaxies. The farther the light travels through expanding space, the more its original character is shifted. This makes the deep universe increasingly difficult to view with ordinary visible light instruments. The edge is therefore shaped not only by raw distance, but by the changing form of the signal itself. The universe hides its remoteness inside the transformation of light. Redshift also changes the emotional scale of distance. A nearby object can be imagined as simply farther down a road of sight. A highly redshifted galaxy resists that simple image. Its light does not merely travel far. It travels through a universe that grows while the journey continues. The gap is not passive. It evolves. The space between source and observer becomes part of the message. This gives the deep cosmos its peculiar calmness. It is not hidden behind a curtain or blocked by a wall. It recedes through process. The farther one looks, the more strongly expansion reshapes what is seen, until remote regions are known less by ordinary appearance than by carefully interpreted spectral traces. In this way, the visible frontier is made not only of faintness, but of stretching, time, and the disciplined reading of altered light. So the universe's apparent edge remains open, yet it becomes harder to reach an observation because light from greater depths arrives, increasingly transformed by expansion. Redshift is the quiet signature of that transformation. It tells astronomers that the large-scale universe grows in separation, that distant galaxies are seen through a history of stretching space, and that the farthest visible realms are not encountered in their original light, but in light altered across cosmic passage. The result is not a final barrier. It is a deepening change in the very signals by which the universe becomes known. The farther outward the visible cosmos extends, the more its light bears the mark of expansion, and the more the apparent edge becomes a horizon written in redshift rather than a boundary drawn in matter. The apparent edge of the universe becomes more exact again when it is described as a particle horizon. This phrase sounds abstract, but its meaning is simple in outline. The particle horizon is the farthest boundary from which any signal could have reached an observer by the present time. Given that the universe has a finite age and that signals travel at a finite speed, in current cosmology, it marks the boundary between the region whose past events have already become observable and the region whose past events have not yet become observable. In that sense, it is one of the clearest scientific meanings of the farthest edge that can presently matter. It is not a material rim, it is not a shell of matter, fire, or dust. It is a limit set by history, by travel time, and by the evolving geometry of the cosmos. This horizon belongs to the broadest record of contact. Earlier sections describe the observable universe as the portion from which light has had time to arrive. The particle horizon expresses that same idea with greater precision. It asks, at this moment, what is the greatest distance from which information can already have reached here? The answer defines a boundary, but it is a special kind of boundary. It does not separate existence from non-existence. It separates what has already entered the observer's past light record from what has not yet done so. This makes the horizon real in physics without turning it into a wall in space. The region beyond it is not established as empty. It is simply not yet in causal contact with the present observer through any signal that has had time to arrive. The phrase particle horizon comes from the older language of cosmology, where particles or signals are traced through expanding space-time. In more modern and careful description, the key idea is not tiny material bodies moving through a fixed arena, but information crossing an evolving universe. A signal emitted near the beginning of cosmic history and travelling ever since defines, in effect, the outer reach of present observability. The horizon is therefore tied to the age of the cosmos, but it is not equal to a simple calculation of age multiplied by the speed of light. That everyday estimate is too small, because the universe expands while the signal travels. The source that emits the earliest reachable light does not remain at the place where it begins. Space stretches during the journey, and the present proper distance to the horizon becomes much larger than a naive age-times-speed estimate would suggest. A standard cosmology review notes directly that the proper distance to the particle horizon is not simply the age of the universe multiplied by the speed of light, but is instead related to how much the universe expands while the signal travels. This gives the particle horizon a quiet but unsettling character. It is the boundary of the observable universe, yet it is not fixed in the ordinary sense. It changes with time. At any given cosmic moment it defines a unique distance, and as cosmic time advances, that distance changes as well. More remote regions can come into observational reach because their signals have had longer to travel. The horizon is therefore not a frozen border painted onto space once and for all. It is a moving surface in space-time, a changing sphere around the observer whose meaning is always tied to a particular moment. A widely cited cosmology review emphasizes exactly this point. The particle horizon at any particular time is a sphere around the observer whose radius equals the distance to the most distant object visible at that time. Because it moves in this way, the particle horizon is better understood as a record of successful arrival than as a line of exclusion. What lies within it belongs to the accumulated history of received signals. What lies beyond it remains outside that received history for now. This makes the horizon less dramatic in appearance than older images of a cosmic border, but more profound in meaning. It is the largest boundary that observation can define without pretending to see beyond what has actually arrived. It is the farthest extent of present causal access to the past. That access may widen as time passes, but at each moment the horizon still tells the same calm truth. The universe does not become known all at once. It becomes known by the gradual arrival of information across expanding distance. There is another important restraint in this concept. The particle horizon is often confused with other cosmic limits, especially with simpler ideas such as a speed boundary or a fixed edge drawn at the place where recession becomes very great. But the particle horizon is not defined by whichever galaxies seem to recede at some chosen rate. It is defined by observability itself, by whether signals have had time to reach the observer. A classic review on cosmological misconceptions stresses that the particle horizon, not the Hubble sphere, marks the size of the observable universe. This matters because it keeps the discussion anchored to information rather than to a misleading picture of galaxies racing through a static void. The true farthest boundary is not the place where motion merely looks extreme. It is the place beyond which no signal has yet arrived. The horizon also behaves in a one-way manner with respect to visibility. Once a region becomes visible by entering the particle horizon, it does not simply fall back out in the sense of having never become observable. A recent review of cosmological horizons states this plainly. Once a cosmic object falls within the particle horizon, it remains within it. That statement gives the horizon a cumulative quality. It marks an expanding archive of accessible past events, rather than a flickering threshold where regions appear and disappear without memory. The visible cosmos builds outward by addition to the observer's accessible record. So in this region of the subject, the farthest edge of the universe becomes neither a wall nor a mystery object, but a rigorously defined horizon. The particle horizon marks the present outer limit from which information can already have arrived. It owes its existence to finite cosmic age, finite signal speed, and the expansion of space during every long journey of light or other radiation. It surrounds the observer without granting that observer any special cosmic status. It grows with time without becoming a material shell. It defines the observable universe without claiming to define the whole of existence. In that quiet precision, the old image of an edge is transformed. What stands farthest out is not a border built into space itself, but the current limit of contact between the observer and the deep past of the cosmos. The farthest visible reaches of the universe are not empty. They contain galaxies whose light begins its journey when cosmic history is still very young, and these remote systems turn the abstract idea of a horizon into something more tangible. Beyond the broad boundary described by the particle horizon, astronomy still asks what kinds of objects stand nearest to that limit in actual observation. At present, among the deepest directly seen structures are galaxies from the era often called cosmic dawn. This phrase refers to the period when the first generations of stars and galaxies begin to form out of the cooling matter of the young universe. Their appearance does not mark the beginning of everything, but it does mark the beginning of a visible luminous order that resembles the later universe in recognizable ways. In this region of the subject, the apparent edge of the universe is no longer described mainly as a horizon of possible contact. It is described as the farthest zone where actual galaxies have been observed, carrying the earliest starlight that current instruments can recover. These galaxies are not seen as they are now. They are seen as they are when the universe is still in its youth, long before the Sun, Earth, or the Milky Way reach their present state. Because light requires time to travel, the deepest galaxy observations are records from the remote past. The farther such a galaxy lies in observational distance, the earlier the stage of cosmic history that becomes visible through it. This makes the farthest galaxies different from nearby examples not only in position but in time. They belong to an earlier universe, one in which structure is still assembling, stars are forming under different conditions, and the cosmic environment has not yet settled into the mature, large-scale pattern seen closer to the present age. Looking toward them is not like looking across a great plain toward a remote but contemporary city. It is more like opening a narrow window into a much younger epoch, where the first substantial islands of light begin to stand out against a still-forming cosmic background. Their light is difficult to detect because nearly everything about the journey works against easy observation. These galaxies are extraordinarily remote. Their light is strongly stretched by expansion. What begins as shorter wavelength radiation when the stars first shine is drawn into longer wavelengths by the time it reaches modern telescopes. Their apparent brightness is extremely low. Not necessarily because each one is small in an absolute sense, but because their great distance spreads the signal thinly across observation. To recover such objects, astronomy requires long exposures, careful filtering, and instruments designed to receive light in the infrared, where much of the ancient radiation finally arrives. This is why the visible frontier of early galaxies remains a technical achievement as much as a conceptual one. The universe does not place a clear sign at the distance where the first galaxies can be found. It hides them in redshift, faintness, and the quiet difficulty of extracting ancient light from background noise. Even when such galaxies are detected, they rarely appear as detailed structures in the ordinary visual sense. Nearby galaxies can show spiral arms, dust lanes, bright clusters, and shaped disks under strong observation. The earliest known galaxies often appear as dim smudges, tiny compact traces, or faint reddish sources whose significance lies less in visual richness than in their position in cosmic time. Their importance comes from what they prove. They show that the universe forms organized stellar systems very early. They show that the visible frontier is populated not only by diffuse radiation, but by actual gravitationally gathered objects. They show that the cosmos at great depth is already becoming structured, already making stars, already shaping the first recognizable forms of galactic existence. This is why the farthest galaxies matter so much to the language of edges. They do not reveal a final boundary. They reveal that near the deepest frontier now reached, the universe is still full of process rather than termination. Cosmic dawn carries a particular calmness because it is neither the first moment of the universe nor the later fully developed age of galaxies. It is an in-between brightness. Before it, the cosmos passes through earlier states in which no stars yet shine. After it, galaxies multiply, grow, merge, and fill space with richer and more familiar structure. The galaxies of cosmic dawn occupy the threshold where darkness begins to yield to stellar light. They belong to the first recognizable chapter in which luminous systems take shape on a large scale. In that sense, they're not merely distant galaxies. They are the earliest presently visible answer to the question of what stands out near the deep frontier of observation. The edge is not bare. It contains the first known lamps of the young universe. This region is also one of careful uncertainty. The farther astronomy reaches, the more strongly interpretation depends on weak signals, model fitting, and painstaking confirmation. A candidate galaxy at extreme redshift may first appear as a source whose distance is estimated from colour and brightness patterns, then later require stronger confirmation through spectroscopy or other detailed analysis. Some early identifications become firmer with time, others are revised. This does not weaken the scientific picture. It reflects the difficulty of working close to observational limits. At the edge of present visibility, evidence often arrives in stages. A faint source becomes a likely galaxy. A likely galaxy becomes a better measured one. A measured one becomes part of the emerging map of early cosmic structure. The visible frontier is therefore not only remote in space and time, it is delicate in method, requiring patience before the youngest known galaxies can be placed securely in the history of the universe. So the apparent edge of the universe, in this sixth region, is best imagined as the domain of the earliest galaxies now seen near cosmic dawn. These objects do not mark a wall. They do not stand at a final border beyond which nothing lies. They stand as the farthest luminous system's current instruments can directly recover, carrying light from a very young cosmos in which the first stellar structures are taking hold. Their faintness, redness, and remoteness do not signify emptiness beyond them. They signify that astronomy is reaching into an earlier chapter, where the universe is only beginning to fill itself with durable light. The frontier here is not an ending. It is the first visible emergence of galaxies from the deep early dark, and it shows that what seems like the edge is already a place where cosmic structure is quietly coming into being. After the first galaxies begin to shine, the young universe enters a long transition in which light is present but does not yet move freely through all of intergalactic space. This region of cosmic history is often described as reionization, a name for the era when the largely neutral hydrogen between galaxies is gradually altered by energetic radiation from the first generations of stars and galaxies. Neutral hydrogen means hydrogen atoms whose electrons remain bound to their nuclei rather than stripped away. In that state, the gas is very effective at absorbing certain kinds of ultraviolet light. The result is often compared to a fog, not because the universe contains clouds like those of Earth, but because radiation from early sources cannot travel across the wider cosmos without being repeatedly blocked, scattered, or absorbed by this widespread neutral gas. NASA explains that before and during reionization, immense amounts of neutral hydrogen surrounding young galaxies block energetic ultraviolet light. While ESA likewise describes large clumps of neutral hydrogen in intergalactic space, absorbing far ultraviolet light from the earliest galaxies. This gives the distant universe a strange half-lit character. Stars exist. Galaxies exist. Light is being made in abundance inside them. Yet the wider medium between these islands of light remains resistant to transparency. The universe has not returned to complete darkness, but neither has it become fully open to long-range luminous travel. It is a cosmos in the act of clearing. The clearing does not happen all at once, and this is what gives the era its distinctive shape. Radiation from young stars does not immediately wash away the neutral fog everywhere. Instead, small transparent regions begin to form around the earliest luminous systems. NASA material describing cosmological reionization presents the process in just this way, with the first stars and small early galaxies creating local transparent regions around themselves as they reheat and ionize the surrounding hydrogen gas. These pockets then grow, overlap, and gradually join into larger transparent volumes. This means the universe during reionization is patchy. Some regions are already becoming clear enough for certain ultraviolet signals to escape, while others remain opaque. The visible frontier is therefore not a smooth advancing shell. It is a scattered and uneven opening of space, region by region, source by source. A galaxy able to carve a transparent bubble around itself does not instantly change the whole cosmos, but it does alter its local surroundings in a way that can eventually contribute to a much broader transition. The image is calm and cumulative. Countless small acts of illumination slowly change the wider medium until the fog retreats from much of the universe. This patchiness matters because it explains why the edge of visibility in the early universe is not determined by distance alone. Two galaxies at similarly remote times may not be equally easy to observe if one lies within a region already cleared enough for its light to escape while another remains embedded in more opaque surroundings. Recent NASA observations with Webb describe galaxies seen while still mysteriously clearing surrounding fog, and both NASA and ESA note that one of the central questions of this era is which kinds of galaxies provide most of the radiation that drives the transformation. Webb results released by NASA in 2025 point toward numerous smaller galaxies as major contributors, while ESA likewise reports evidence that dwarf galaxies may play a dominant role in reionizing the universe. Yet uncertainty remains in the details. Observations indicate that early stellar populations and young galaxies are central to the process, but it remains uncertain exactly how the contribution is divided among small galaxies, larger galaxies, and other energetic sources across different stages of the era. That uncertainty belongs naturally to a frontier subject. The universe during reionization is studied indirectly through faint light, spectral signatures, and the changing transparency of intergalactic hydrogen, so the broad picture is strong even where the finer accounting is still being refined. What gives this era its deeper importance is that it changes the character of the universe from locally luminous to widely transmissive. Before enough of the hydrogen between galaxies is ionized, much of the ultraviolet record of early cosmic life cannot travel far. After enough of that hydrogen is ionized, the universe becomes much more open to radiation crossing large distances. ESO describes this clearly, noting that when the first stars and galaxies form, the universe is filled with neutral hydrogen gas that absorbs ultraviolet light, and that as ultraviolet radiation from these early galaxies ionizes the gas, the universe gradually becomes transparent to such light. In this sense, reionization is not merely another event in cosmic history. It is a change in the transparency of the medium itself. The apparent edge of the universe is affected by it because what can be seen from deep time depends not only on whether light exists, but on whether the space between source and observer allows that light to pass. So this seventh region of the subject is neither the first appearance of light nor the oldest light of all. It is the long cosmic clearing in which the early universe moves from a state of widespread neutral obscuration toward one of much greater openness. The first galaxies do not stand alone against a fully transparent background. They work upon their surroundings. They alter intergalactic space. They carve clearings into the hydrogen fog and slowly join these clearings together. In that calm and gradual transformation, the universe does not reveal an edge as a wall or a rim. It reveals an edge that softens because the medium itself changes. the deeper past becomes more visible only as the fog yields, and the yielding comes through the accumulated radiation of the first luminous structures. Reionization is therefore the era in which the young universe learns to let its own early light travel farther, turning scattered local brightness into a broader cosmic transparency and making the distant frontier less a fixed border than a slowly opening field of view. Beyond the farthest galaxies and beyond the long clearing of the early cosmic fog lies a much deeper visible frontier, one that's not made of stars or galaxies at all. It is made of radiation released when the young universe first becomes transparent enough for light to travel freely across great distances. This radiation is called the cosmic microwave background. The phrase sounds technical, but its meaning is direct. It refers to a background glow of ancient light that fills all of space and arrives from every direction. It is not concentrated in one cluster or one remote corner of the sky. It surrounds the observer completely. In this region of the subject, the apparent edge of the universe takes the form of a luminous surface, sometimes called the surface of last scattering. That phrase describes the time when light and matter stop interacting so constantly that photons remain trapped in the hot early plasma. Once the universe cools enough, that trapping weakens and light begins to move more freely. What is seen today as the cosmic microwave background is the stretched and cooled remnant of that first widely liberated light. This surface is not a shell built from solid material. It is a surface in time, and because light takes time to travel, it also appears as a surface in space around the observer. Looking outward toward it in any direction means looking back to an era when the universe is only about 380,000 years old. This is very early in cosmic history, long before stars, galaxies, planets, or any later structure familiar to the present universe. Yet it is not the absolute beginning. It is the earliest epoch from which ordinary light can reach modern observers directly. That is what gives the cosmic microwave background its special place. It is not the first event in the universe. It is the oldest directly seen light, farther back than this. Ordinary electromagnetic radiation does not yet travel freely through the cosmic medium in a way that allows a direct image of earlier conditions to arrive unchanged. The phrase last scattering helps clarify the character of this frontier. In the hot early universe, matter and radiation remain tightly coupled. Light is repeatedly scattered by free charged particles, especially electrons, so that the cosmos behaves less like a transparent volume and more like a glowing fog. A photon does not travel far before interacting again. Then, as the universe expands and cools, electrons combine with nuclei to form neutral atoms. This process is often called recombination, though in plain language it means that matter changes from a charged plasma into a neutral gas. Once that transition occurs, radiation is no longer scattered at the same overwhelming rate. Photons can then move much more freely across space. The cosmic microwave background comes from that release. It is the ancient light that last scatters significantly before beginning the long journey toward the future universe. Seen from the present, this makes the cosmic microwave background look like a boundary to ordinary sight. A telescope aimed deeper and deeper into the cosmos can recover earlier galaxies, then the era of reionization, and then, in a still deeper sense, this ancient radiation itself. But it cannot use ordinary light to form a direct visual record of the universe before this surface, because earlier than this epoch the medium remains too opaque. The background therefore acts like a veil. It is luminous rather than dark, but it still limits direct sight. This is one reason the edge of the visible universe is often misunderstood. It is not an empty rim where matter stops. It is a bright boundary beyond which ordinary light cannot simply pass. The farthest direct image is not a final wall of objects. It is a record of the moment when the universe first becomes transparent enough to leave such a record at all. The light of the cosmic microwave background no longer appears as visible light, because the universe expands enormously during its journey. What begins as much hotter radiation is stretched over cosmic time into microwave wavelengths. This is why the background is not seen by the eye as a glowing sky. It requires instruments sensitive to microwaves and related frequencies. When measured, it appears extraordinarily uniform across the heavens, which means that the early universe at this stage is strikingly smooth on very large scales. Yet it is not perfectly smooth. Tiny variations exist in temperature and density across the background. These variations are extremely small, but they matter deeply. They preserve a map of early unevenness in the cosmos, a faint pattern of slightly warmer and slightly cooler regions that correspond to slight differences in matter distribution. In this section, however, their importance lies first in what they reveal about the surface itself. The cosmic microwave background is not random noise. It is a structured relic, carrying an image of the young universe at the moment the visible veil forms. Its calmness is one of the most unsettling things about it. The oldest directly seen light does not arrive as chaos. It arrives as an almost uniform glow from all directions, indicating that the early universe at that stage is extraordinarily even. This smoothness can feel surprising because the later universe is full of galaxies, clusters, vast gaps, and the richly varied architecture of the cosmic web. Yet at the surface of the microwave background, most of that later contrast is not yet present in developed form. The cosmos is still young, still simple in its largest visible face, still holding only faint traces of the structure that will grow much later. The visible edge is therefore gentle in appearance. It is not ragged with countless large objects. It is broad, smooth, and nearly featureless to first inspection, like a distant luminous mist that surrounds all directions equally. So this eighth region of the subject brings the apparent edge of the universe into its deepest directly visible form. The cosmic microwave background is the oldest light that can be observed directly by ordinary electromagnetic means. It comes from the epoch when the universe cools enough for light to move freely, creating a surface of last scattering that now appears around the observer as a vast, ancient boundary of visibility. It is not a wall, not a material shell, and not the absolute beginning. It is the earliest luminous screen that present astronomy can see across the whole sky. Beyond it, ordinary light cannot yet carry a direct image from earlier times. In that sense, the background stands as the last visible veil, the calm, bright frontier where the universe first allows itself to be seen at all. Before the universe becomes transparent enough to release the ancient light now seen as the cosmic microwave background, it exists in a very different state. It is not filled with stars, galaxies, or clear empty reaches between luminous objects. It is a hot, dense, glowing plasma. A plasma is a state of matter in which electrons do not remain bound to atomic nuclei, so the gas is not neutral in the ordinary sense. Instead, free electrons and bare nuclei move within an intensely radiant environment. In this condition, light does not travel across great distances in a straight and lasting way. It is repeatedly scattered by the free charged particles around it. The universe is full of radiation, but that radiation cannot yet form a clear outward view. The cosmos shines, yet it is opaque. This is the strange calm of the primordial plasma. The young universe is bright everywhere and visible nowhere in the later sense of transparent distance. The opacity of this state is not caused by dust. clouds, or darkness. It arises from constant interaction. A photon moving through the early plasma does not continue freely for long before it meets a free electron and changes direction. Then it travels a little farther and scatters again. This repeated scattering traps radiation within the plasma in a statistical sense. Light remains present at every point, but it cannot stream cleanly across the universe in a way that preserves a simple visual record from one region to another. The effect is comparable, in a loose and limited way, to trying to see across a very dense fog while every beam of light is deflected again and again before reaching any distant point. The fog comparison remains imperfect because the early universe is vastly hotter, simpler in composition, and far more uniform than any earthly mist. But it helps reveal the core idea. The young cosmos is not empty and dark. It is radiant and concealed at once. This state belongs to a universe still too hot for ordinary neutral atoms to survive. Electrons carry too much energy to remain attached to nuclei for long. Even if they combine briefly, collisions and energetic radiation can separate them again. Hydrogen, which will later dominate the ordinary matter of the universe in neutral form, does not yet behave as stable atomic hydrogen. Helium nuclei are present as well, but the wider medium remains ionized. The matter and radiation of the cosmos are therefore tightly coupled. They influence one another continuously. Radiation pushes on matter, matter scatters radiation. The universe at this stage behaves less like a set of separate contents placed in space, and more like one interwoven thermal medium. Heat, light, and charged particles belong to the same broad condition. Nothing yet resembles the transparent deep sky familiar to later cosmic time. The scale of this opacity is difficult to hold in the mind because it covers the whole observable universe of that era. On Earth, opacity usually belongs to a local thing. A cloud blocks a mountain, smoke fills a valley, mud darkens water. In the primordial plasma, opacity is not local. It is cosmic. There is no clear region just beyond the cloud, because the cloud is the condition of the universe itself. Every direction leads into the same hot luminous medium. Every line of sight is short-lived before it dissolves into repeated scattering. That is why the cosmic microwave background marks such an important boundary in later observation. It represents the moment when this universal opacity softens enough for light to begin a freer journey. Before that moment, ordinary electromagnetic sight cannot simply pass deeper inward. The universe is not yet ready to be seen across distance. Yet this opaque state is not static. It changes because the universe expands. Expansion lowers density and temperature over time. The primordial plasma does not remain forever at its earliest intensity. It cools gradually as space stretches. This cooling is not a local breeze or a contact with some colder outside. It is a global consequence of cosmic expansion. As the universe grows, the energy conditions shift. Particles move into a less crowded environment. Radiation loses energy through redshifting. Matter and light remain strongly linked, but the balance slowly changes. This long quiet drift toward lower temperature is what eventually allows electrons and nuclei to combine more durably into neutral atoms. Once that happens widely enough, the constant trapping of photons weakens, and transparency begins to emerge. But within this ninth region of the subject, the universe has not yet crossed that threshold. It remains in the era before clear release, still enclosed in its own glowing thickness. There is something deeply unsettling in the fact that the early universe is brightest when it is least visible in the later observational sense. One might expect the most radiant universe to be the easiest one to see through. The opposite is true here. The intense heat keeps matter ionized, and ionized matter keeps radiation from traveling freely. Abundance of light does not produce openness, it produces entanglement. The young universe contains no distant luminous objects because distance itself has not yet become optically meaningful in the same way. Radiation belongs to the local surroundings everywhere, constantly exchanged, constantly redirected. The cosmos is immersed in light and yet offers no transparent depth. This state also gives the early universe a remarkable simplicity of composition. It is not chemically rich. It does not contain the heavy elements made much later in stars. It consists mainly of the lightest ingredients, arranged in a hot plasma sea shaped by temperature, density, radiation, and expansion. That simplicity matters because it means the opacity is not caused by complicated later astrophysical processes. It is a basic outcome of the universe's youth. The medium is too hot and too charged for long-range optical freedom. Its concealment is fundamental, not accidental. It belongs to the earliest large-scale physical state from which the later transparent universe must emerge. So this ninth region of the subject stands behind the cosmic microwave background as the opaque primordial plasma itself. It is a universe filled with free electrons, bare nuclei, and trapped radiation, glowing intensely while refusing clear sight. Light exists everywhere within it, but ordinary light cannot yet carry a stable image across its depths, because scattering is too constant and the medium too dense and ionized. Space is already expanding, and that expansion is already preparing the way for transparency, but the threshold has not yet been crossed. The apparent edge of the visible universe therefore opens onto a deeper condition that is not dark emptiness and not a physical wall. It opens onto a hot, radiant, opaque plasma, a cosmos before clear seeing, when the universe still holds its light close and has not yet begun to let it travel freely into the ages that follow. The ancient light of the cosmic microwave background appears nearly smooth, but not perfectly so. Across that calm surface lie minute variations in temperature and density, so small that they barely disturb the overall uniformity, yet large enough to matter for everything that follows. These tiny irregularities are the seeds of structure. They do not look dramatic. They do not resemble galaxies, clusters, or the long filaments of the cosmic web. At this stage, there are only slight differences from place to place, regions where matter is a little denser or a little thinner than average. But gravity is patient. Given enough time, even a very small excess can begin to draw in more matter, while a slightly emptier region can give up matter to its surroundings. In this way, the nearly uniform early universe contains within itself the first quiet map of later complexity. The strength of these seeds is remarkable precisely because it is so slight. The young universe at the time of the microwave background is extraordinarily even on large scales. That smoothness remains one of the deepest facts in cosmology. Yet it is not perfect smoothness, and perfection would leave little room for later structure to grow. A universe with no variations at all would not easily separate into dense knots and emptier reaches. There would be no preferred places for matter to gather. The tiny unevenness seen in the ancient background light therefore carries unusual importance. It shows that the early cosmos begins with just enough difference to break exact uniformity without destroying overall balance. The universe is calm, but not identical everywhere. That gentle departure from sameness becomes the opening through which all later large structure emerges. These early differences are best understood as differences in density. A denser region contains slightly more matter than the surrounding average. A less dense region contains slightly less. Once the universe becomes transparent and matter can respond more freely to gravity over time, These differences begin to grow. The process is slow. Nothing like a sudden collapse happens everywhere at once. Instead, matter moves under gravitational attraction, with slightly denser regions exerting slightly stronger pull. Because they contain a little more mass, they attract more material. As they attract more material, their pull becomes stronger still. The denser regions therefore tend to grow denser. Meanwhile, regions that begin with slightly less matter tend to lose relative importance. They become the beginnings of the wide lower density spaces that later appear between the great luminous structures of the mature universe. This is the first quiet sorting of cosmic matter. The ordinary matter that later forms stars, gas clouds, and galaxies does not act alone in this story. Observations indicate that most matter in the universe is dark matter, a form that reveals itself through gravity rather than through ordinary light. Dark matter does not shine, and it does not interact with radiation in the same way ordinary matter does. This gives it a special role in structure formation. Before ordinary matter can gather efficiently into later visible systems, dark matter can already begin building a gravitational framework. In plain terms, it forms the deeper scaffolding into which ordinary gas later falls. This does not make the early universe chaotic. It makes it quietly layered. The visible matter of the later stars and galaxies grows within a larger unseen pattern of gravitational structure that begins from the same tiny primordial differences. Because the initial variations are so small, the growth of structure takes long stretches of time. The universe does not leap from faint irregularity to full galactic richness in a single movement. It proceeds gradually. Small, denser regions become more pronounced. They merge, deepen, and pull in additional matter. Larger patterns begin to emerge from the accumulation of smaller ones. Over immense time, this growth produces a universe in which matter is not spread evenly like mist, but arranged into knots, sheets, and filaments separated by vast lower density regions. The cosmic web, with its long strands and clustered intersections, begins here in seed form. It is not placed onto the universe from outside. It grows from the tiny original departures from uniformity that the ancient background still records. There is something deeply calm in the scale of this transformation. The early seeds are almost invisible in strength, yet they govern the broad architecture of everything that comes later. Great clusters of galaxies, immense filaments stretching across millions of light years, and the vast dark regions between them all arise from differences so faint that they first appear almost negligible. This gives the universe a kind of quiet memory. The mature cosmos still bears the consequence of conditions present in the first observable light. Later grandeur is already encoded in early subtlety. What looks nearly featureless from one point of view is already rich with future pattern from another. The seeds also explain why the ancient universe can be both smooth and fertile. Smoothness alone might suggest sterility, a cosmos too even to produce structure. The tiny fluctuations prevent that conclusion. They preserve order while allowing growth. They are small enough for the universe to remain broadly uniform, yet large enough for gravity to act upon them across time. This balance matters. Too much unevenness would yield a much rougher early universe. Too little would leave later structure weak or absent. The observed pattern sits in the narrow middle where calm and complexity can coexist. So in this 10th region of the subject, the edge of the visible universe reveals not a final boundary, but the earliest blueprint of later cosmic form. The tiny variations in the ancient plasma, preserved in the microwave background and expressed as slight differences in density, become the seeds from which galaxies, clusters, and the cosmic web eventually grow. Gravity deepens them, dark matter strengthens their scaffolding. Time enlarges their consequences. The universe that later appears full of vast structures does not begin with grand visions already formed. It begins with minute departures from sameness, almost imperceptible at first, but sufficient to shape the entire large-scale architecture of the cosmos. Behind the smoothness of the observable universe lies one of the most influential ideas in modern cosmology. It is called inflation. In simple terms, inflation is the proposal that in the earliest instance of cosmic history, long before atoms, stars, or galaxies exist, the universe passes through a brief period of extraordinarily rapid expansion. This expansion is not the ordinary slower growth of cosmic space described in later epochs. It is a far more dramatic stretching of space itself, happening in a tiny fraction of a second. The idea matters because it offers a way to understand why the visible universe appears so even on the larger scales, and why the geometry of space appears so close to flat. Without such an episode, the calm, broad uniformity of the cosmos can seem much harder to explain. The first part of the puzzle is smoothness. The cosmic microwave background shows that regions of the early observable universe, lying in widely separated directions, have nearly the same temperature. Yet in a simple, non-inflationary picture, those regions appear too far apart to have shared enough information early on to settle into such close agreement. Inflation changes that picture by proposing that the region now visible across the sky once occupies a much smaller and more tightly connected volume. Before the rapid stretching begins, the patch that later grows into the observable universe remains small enough for its contents to influence one another more easily. Then inflation enlarges that small connected patch enormously. The later universe therefore appears smooth across vast distances, not because distant regions somehow adjust themselves across impossible gaps, but because those regions originate from a much smaller domain that is already more uniform before the great stretching occurs. This is one of the quiet strengths of the inflationary idea. It does not place a wall at the edge of the universe or add a new visible object there. It changes the early conditions under which the later observable universe comes to exist. A small region becomes huge. What now seems spread across impossible scales once belongs to a more intimate causal neighborhood, meaning a neighborhood in which influences can pass from one place to another. Inflation therefore addresses the unsettling fact that the visible universe looks too coordinated across distance. It suggests that the coordination comes first, at small scale, and that the large scale comes later through expansion. The second part of the puzzle is flatness. On the largest scales, measurements indicate that the geometry of the observable universe is very close to flat. Flat in this context does not mean flat like a sheet laid on a table. It means that space, when examined over immense cosmic distances, does not show strong overall curvature. In a universe with strong positive curvature, large triangles would not behave in the familiar way, and the overall geometry would bend back upon itself more noticeably. In a universe with strong negative curvature, space would bow outward in a different manner. Observations instead show that the large-scale geometry lies very close to the boundary between those possibilities. Inflation offers a natural reason for this. When something curved is stretched enough, the local region begins to look flatter. A small patch on the surface of a sphere can appear nearly flat if viewed closely enough. In a related but much deeper cosmological sense, inflation can stretch the geometry of the early universe so greatly that any initial curvature becomes much less visible within the observable domain. The universe does not need to begin perfectly flat in every respect. Rapid stretching can make it appear extremely flat across the vast region now accessible to observation. There is also a third calm consequence of inflation. The early universe, even after such enormous stretching, does not become perfectly featureless. Tiny quantum fluctuations, meaning minute natural variations present in the earliest physical fields, can be stretched outward as well. What begins as microscopic irregularity can become macroscopic difference after inflation enlarges space. These stretched variations can then act as the first seeds of later structure, eventually contributing to the formation of galaxies and the larger cosmic web. In this way, inflation does something subtle. It explains why the universe is broadly smooth while also allowing it to contain just enough unevenness for structure to grow. Too much irregularity would leave the early universe rough and disorderly. Too little would leave it sterile. Inflation offers a framework in which both smoothness and small departures from smoothness can arise together. Yet inflation remains a proposal about an era that cannot be watched directly in the ordinary sense. No telescope observes the inflationary event itself as a visible scene. The evidence is indirect. Cosmologists infer inflation because many observations fit well with the kind of universe inflation tends to produce. The large-scale smoothness of the cosmic microwave background, the near-flat geometry of space, and the pattern of primordial fluctuations all sit comfortably within the inflationary framework. This is why inflation becomes the leading description of the earliest known expansion phase in many modern accounts of cosmology. But it is still described carefully. Observations are consistent with inflation and strongly motivate it, yet the precise mechanism behind it remains uncertain. That uncertainty matters. Inflation is often spoken of as though it were a single finished theory, but in practice it is better understood as a family of related models built around the same central idea of brief accelerated early expansion. Different versions describe that expansion through different fields, different potentials, or different transitions into the later hot dense universe. The broad picture is compelling. The detailed engine is not settled. Science therefore separates the success of the general inflationary framework from the unresolved question of exactly what physical process drives it and exactly how it begins and ends. This is one of the quiet disciplines of cosmology. A powerful explanatory idea can be widely used without being treated as complete in every underlying detail. So in this 11th region of the subject, the apparent edge of the universe gives way to a deeper explanation of why the visible cosmos looks the way it does. Inflation does not create an edge. It helps explain why the observable universe appears smooth across vast scales, why space appears so nearly flat, and how tiny early variations can survive inside that smoothness to become the seeds of later structure. It transforms the image of the early universe from a simple static beginning into a brief era of enormous stretching, when a very small connected region becomes the immense visible domain known today. The result is not a final answer to everything beyond the edge, but it is one of the central ways modern cosmology understands how the observable universe acquires its calm, large-scale form at all. Space can have shape without having shoreline, and this is one of the deepest corrections modern cosmology makes to ordinary intuition. In daily life, shape and boundary usually seem inseparable. A room has walls, a field has edges, a lake meets land. Human thought is trained by surfaces that end, so when it hears that the universe may be curved or flat, it often imagines a vast object floating somewhere with an outside and a rim. But geometry at cosmic scale does not need to behave this way. The geometry of space describes how distances, angles, and straight paths behave within the universe itself. It does not automatically imply that space sits inside a larger container with a marked outer border. This is why a universe can be finite and still have no edge. or appear flat across enormous regions without being a sheet suspended in emptiness. NASA materials use the analogy of the surface of a balloon to show how a space can expand and possess no edge within the surface itself, while ESA explanations of cosmic geometry describe flat, open, and closed possibilities in terms of curvature rather than in terms of a physical wall. A flat universe is the easiest case for the mind to misread because the word flat carries strong ordinary associations. It suggests a plane, a tabletop, or an endless floor. In cosmology, however, flat means that on large scales space follows the familiar rules of Euclidean geometry to a very high approximation. Straight paths remain parallel in the expected way, and large triangles behave as ordinary intuition from school geometry would suggest. But this local or large-scale flatness does not by itself force the whole universe to have an edge, nor does it by itself prove that the whole universe is infinite in every global sense. It means first that measurable spatial curvature appears extremely small within the observable domain. NASA educational material notes that the universe appears to be flat, while ESA descriptions of the density and geometry relation explain that a universe at critical density is flat. Modern observational results from Planck are widely described by ESA as showing an almost perfect universe, with measurements consistent with very small spatial curvature. Flatness therefore describes the measured behavior of geometry across the visible cosmos, not the existence of a cosmic floor with an outer ledge. Positive curvature changes the picture without creating an edge. The ordinary analogy is the surface of a sphere. The surface area of a sphere is finite, yet a traveller moving along that surface does not encounter a boundary where the surface stops. There is no final line painted around it. One can continue moving and eventually return to the starting place. NASA's Starchild material uses just this kind of idea, explaining that a positively curved universe is not infinite but has no end, just as the area on the surface of a sphere is finite but has no point that can be called the end. The analogy has limits because the real universe, if positively curved, would not be the two-dimensional surface of an ordinary ball, but a three-dimensional space with analogous properties. Even so, the lesson holds. Finite does not mean bounded by a wall. A space can close on itself geometrically rather than terminate physically. In that case, the universe would possess extent without possessing an edge that could be reached and crossed. Negative curvature also lacks a border in the simple sense. In a negatively curved geometry, straight paths tend to diverge more strongly than they would in flat space, and large triangles have angle behavior different from familiar Euclidean expectations. NASA educational material describes this as space with negative curvature, and ESA explanations classify such an open geometry as one of the broad possibilities allowed by cosmological models. Yet once again, the key point is not a boundary line. Negative curvature changes how space behaves internally. It alters the relation between distance and angle, circumference and radius, path and separation. It does not require that somewhere far away there must be a final cliff where the universe ends. The mind searches for an edge because curvature sounds like bending of an object in a larger place. But cosmological curvature belongs to space itself. It is intrinsic rather than imposed by an outside frame that must be entered into the picture. This is why the phrase edge of the universe becomes so misleading at the level of geometry. Curvature addresses how space is structured, not where an outside begins. A positively curved universe can be finite and edgeless. A flat universe can appear unbounded across all measured scales. A negatively curved universe can expand through its own geometry without presenting a final border. In each case, the important scientific question is how distances and large-scale relations behave, not where a traveller would find a cosmic wall. NASA's Imagine the Universe material states directly that the balloon analogy has no edge to it, and that what lies outside is undefined in that picture. That statement captures the discipline of the subject. Geometry can be meaningful without an external stage being physically specified. The universe need not be an object placed in a larger room for its curvature to be real and measurable. Observations add one final calm restraint. Current measurements indicate that the observable universe is very close to flat, or at least that any overall curvature is extremely small within the region that can be measured well. ESA's Planck material describes a universe whose large-scale properties are consistent with this near-flat picture, but even this does not restore an edge. A nearly flat measured geometry still says nothing like a visible rim has been found. It says instead that the large-scale structure of space, as far as present evidence reaches, behaves with extraordinary geometric gentleness. So in this 12th region of the subject, the universe loses another false boundary. Space may be flat, positively curved, or negatively curved in its large-scale geometry. Yet none of these possibilities requires a physical border where reality stops. Shape remains. Edge does not necessarily follow. The geometry of the cosmos describes how space holds together within itself, and in that self-contained structure the universe can have form without shoreline, extent without boundary, and curvature without any final wall at all. Geometry describes how space behaves locally and on large scales, but topology asks a deeper and more global question. It asks how space is connected as a whole. Two spaces can share the same local geometry and still differ in their overall connected form. This difference is subtle, and it is one of the reasons the universe can remain so difficult to picture clearly. A space may appear flat in local measurement, and yet still possess a global structure that closes back on itself in a way not immediately visible within any limited region. In plain terms, the universe may behave normally in every measured direction, and still have a larger connected pattern beyond what present observation can easily reveal. Topology is therefore not about whether space curves strongly in one obvious way or another. It is about whether the whole of space has a repeating, wrapped, closed, or otherwise connected form that can remain hidden even when local measurements appear simple. This is where the old habit of imagining an edge becomes especially misleading. A finite universe does not need to end at a border. If space is connected in the right way, movement through it could continue without ever encountering a wall, much as motion across the surface of a sphere continues without reaching a final ledge. But topology allows possibilities even more subtle than that familiar image. A space can be flat in local behavior and still be finite if its opposite directions connect. In such a case, a traveller moving far enough in one direction could in principle return from another direction without ever crossing an edge. The space would not terminate, it would wrap. This sounds unusual because daily life rarely presents fully self-connected three-dimensional spaces. Yet the idea is mathematically natural. It shows that finite and unbounded are not opposites. A space can contain a limited total volume while offering no outer rim at which it stops. This possibility matters because current observations do not yet reveal the full global form of the universe with certainty. The observable universe is vast, but it is still only the part from which signals have had time to arrive. The whole universe, if larger than the observable region, may contain topological features too broad to detect within the cosmic volume now accessible to measurement. This means cosmology can often constrain topology more easily than it can determine it outright. Science can ask whether space seems to repeat patterns in the sky, whether distant regions might be multiple views of the same physical place, or whether the microwave background carries signatures consistent with certain compact topologies. But absence of clear evidence for a simple repeating pattern does not immediately settle the whole question. It may mean that if the universe is topologically compact, its characteristic scale lies beyond the observable region, or that its connected form is more subtle than the simplest repeating models. The cosmic microwave background becomes especially important in this search because it provides the oldest full-sky light now available. If the universe wraps around itself on a scale not too much larger than the observable domain, then light from one physical region might reach the observer along more than one route. In principle, this could create repeating circles, matched temperature patterns, or other geometric echoes in the background sky. Cosmologists have searched for such signs. These searches are careful because the expected patterns can be weak, distorted by later cosmic effects, or absent if the topological scale is too large. So far, observations do not provide strong accepted evidence that the observable universe is small enough and topologically arranged in a simple way that produces obvious repeated sky patterns. That result narrows some possibilities, but it does not force the whole universe to be infinite. It only means that if space is globally closed or wrapped in one of those forms, the scale is likely beyond easy direct detection from the present observational patch. This uncertainty leaves modern cosmology in a disciplined middle ground. On one side lies the possibility that the universe is effectively infinite, extending far beyond the observable horizon without closure at any accessible scale. On the other lies the possibility that the universe is finite but unbounded, with a global connected form larger than the region now seen. Both broad options remain compatible with the absence of a physical edge. Both remove the idea of a final wall. The difference between them is not whether one ends and the other does not. The difference is whether space, taken as a whole, eventually closes or repeats in some connected manner, or continues outward without global closure at all. This is a deeper question than ordinary size because it concerns the very pattern of existence rather than the distance to a boundary. There is a quiet emotional change that comes with this idea. The universe stops behaving like a container and begins behaving like a connected structure whose whole may remain hidden, even when its local properties are measured with great precision. Human thought often wants to know whether the cosmos is large or small, finite or infinite, inside or outside something else. Topology softens those habits by showing that some of these oppositions are too crude. Finite need not imply bounded. Endless travel need not imply infinite extent. Familiar geometry need not reveal the total connectedness of the whole. The universe may therefore be more complete than intuition expects, and less box-like than language usually suggests. This region of the subject also clarifies why the phrase beyond the edge can mislead even when used poetically. If space has a global topology that closes or wraps, then there may be no beyond in the ordinary directional sense. There may be farther regions, unseen regions, and regions outside present observation, but not an outer side of space waiting after a final border. Even in an effectively infinite universe, the word beyond remains safer when it means beyond observation rather than beyond a cosmic wall. Topology teaches restraint. It tells cosmology not to assume that what cannot yet be mapped must lie past an edge. It may instead belong to a larger connected whole whose form surpasses the visible patch. So in this 13th region of the subject, the universe is approached as a total connected structure rather than merely a visible expanse. Topology opens the possibility that space may be finite yet unbounded, flat yet wrapped, or simply far larger than the observable domain without any detected closure. Present evidence does not show a physical edge. it also does not fully reveal the whole connected form of the cosmos. The result is a calm and exact uncertainty. The universe may possess a global pattern that closes on itself, or one that extends far beyond present reach. But in either case, the old image of a final border remains unnecessary. The whole may be limited or unlimited, but it need not end. Beyond the observable universe lies the most cautious form of scientific beyond. It is not a second realm made of different laws. It is not a proven outside surrounding the cosmos like air around a vessel. It is, in the most conservative picture, simply more universe extending past the present horizon of observation. This idea begins with restraint. The observable universe is defined by what light and other signals have had time to reach. That definition sets a boundary on knowledge from here, but it does not, by itself, set a boundary on existence. Once that distinction is kept clear, the meaning of beyond changes. It no longer suggests a step across an edge or a crossing into another kind of place. It suggests continuation without access, a farther expanse that remains hidden not because it is sealed away by a wall, but because no signal from it has yet arrived. This is one of the quietest and strongest conclusions in cosmology. The horizon marks a limit of observation, not a demonstrated termination of space. Nothing in the standard description of the observable universe requires the cosmos to stop where observation stops. On the contrary, the large-scale smoothness of the universe, the near uniformity of the cosmic microwave background, and the success of cosmological models that treat the visible region as part of a broader expanding whole, all encourage the idea that what lies beyond the horizon is more of the same general universe. That does not mean every unseen region is identical in detail. Galaxies, clusters, empty regions, and local histories can differ from place to place. But it does mean that the simplest well-grounded expectation is continuity rather than abrupt ending. The universe does not give signs, at the observable limit, of approaching a terminating border. It gives signs of receding accessibility. This expectation is strengthened by the cosmological principle, the working assumption that on sufficiently large scales the universe is broadly homogeneous and isotropic. Homogeneous means that space, when averaged over great enough distances, has no special preferred place. Isotropic means that it appears broadly similar in all directions. These ideas do not claim that every local region is the same. They do not erase galaxies, clusters, voids, or the rich unevenness of smaller scales. They speak instead about the very large statistical structure of the cosmos. If the observable universe is one large patch of such a cosmos, then the most natural extension beyond its horizon is not emptiness or an ending, but additional regions governed by the same broad physical rules. The unseen universe, in that view, is not a separate category of reality. It is the continuation of a pattern already seen. There is an important discipline in this reasoning. Science does not directly observe those farther regions, so it does not describe them with the same certainty used for nearby galaxies or measured radiation. It infers them. The inference is not arbitrary. It grows from models that successfully describe the visible universe and from the absence of evidence for a terminating edge. Yet it remains an inference. Observations indicate that the horizon is a limit of current causal contact, and the standard framework strongly suggests that space continues beyond it. But direct evidence from these specific unseen regions is unavailable by definition. This combination of confidence and humility is central to the subject. Cosmology can say that continuation is the most conservative expectation, while also admitting that exact details beyond the horizon are not directly mapped. The beyond of the observable universe is therefore a beyond of hidden ordinariness. That may sound less dramatic than older imaginative visions of a final boundary, but it is more unsettling in its own way. A wall would end the question. Continuation preserves it. If space extends beyond the horizon, then the visible universe is not the whole stage but only one accessible patch within a much larger totality. That totality may be vastly larger than what can ever be seen from Earth. It may contain innumerable galaxies and structures forever outside present contact. Some of those regions may once have causal relation to the patch now observed in the deep early universe. Others may remain unreachable for ages beyond ordinary conception. Yet none of this requires a change in physical kind. The hidden universe can remain part of the same cosmic fabric, while still being permanently or effectively inaccessible from here. This makes the edge of observation feel less like a barrier and more like a curtain drawn by time and light. The curtain does not prove that the stage ends behind it. It only prevents present viewing. In everyday life, a curtain usually implies that something continues beyond sight, and this ordinary intuition, in a rare reversal, serves cosmology well. The observable universe does not behave like a room whose far wall has been reached. It behaves like a field of vision limited by the age of the cosmos and by the travel time of signals. The farther regions remain dark not because existence has been cut off there, but because communication has not yet connected them to the observer. The continuity beyond the horizon also helps explain why cosmology can describe the universe with global equations and large-scale models, even though only one finite region is observed directly. These models do not pretend that all details beyond the horizon are known. They extend the same lawful behavior that successfully accounts for the visible cosmos. Expansion, matter content, radiation history, and large-scale geometry are treated as properties of the universe beyond the visible patch, because no evidence requires those properties to cease abruptly at the horizon. The unseen universe is thus approached as an extrapolated continuation of the seen one. This is not proof in the strictest direct sense. It is the most conservative and coherent reading of the evidence available. So in this 14th region of the subject, what lies beyond the edge of the observable universe is best described, not as an outside, but as more universe beyond present view. The horizon does not mark the end of space, it marks the end of received signals. Beyond it, current science most carefully expects continuing cosmic expansion, further regions of matter and radiation, and the ongoing large-scale fabric of the same universe whose near patch becomes visible from Earth. Exact details remain unobserved, and certainty stops where direct contact stops. But the strongest disciplined answer remains simple. Beyond the observable edge, there is most likely not a border, there is continuation, hidden by horizon rather than ended by wall. At the deepest inward point of this subject, the language of edge begins to fail entirely. The question is no longer where the universe ends in visible space, or what region lies beyond the present horizon of light. It becomes the more difficult question of whether the idea of an outside has any scientific meaning at all. In standard cosmology, the universe is not treated as an object sitting inside a larger ordinary space, in the way a stone sits in air or a planet hangs in a wider void. It is the total system of space-time, matter, radiation, and physical law as far as the model describes them. For that reason, asking what lies outside the universe can become undefined rather than unanswered. NASA educational material makes this point directly, noting that in the balloon analogy there is no edge to the universe, and that what lies outside is undefined, while older NASA cosmology guidance likewise explains that it is not logically necessary to imagine the universe expanding into something external. This does not mean the question is foolish. It means the everyday habits behind the question come from the wrong scale of experience. Human thought expects containers and surroundings. A house stands in a landscape. A cloud hangs in a sky. A galaxy moves through intergalactic space. At each of those levels, one thing can be asked to sit within another larger thing. But when cosmology speaks about the universe as a whole, the usual surrounding space is already part of the thing being described. Space is not the backdrop outside the universe in the standard picture. Space is part of the universe. Time is part of the universe as well. So when the mind searches for an outer room into which the cosmos expands, it often carries a local earthly image into a domain where that image no longer fits. The result is a boundary that intuition wants but physics does not require. From this point, science divides into two levels of confidence. The first is strong and conservative. It says that the observable universe is not the whole of what most cosmological models describe, and that beyond the horizon there is likely more universe, not an edge or a proven outside. The second is weaker and more speculative. It asks whether the total reality described by physics might include domains beyond even our own cosmic region, perhaps with different large-scale conditions, perhaps born from inflationary processes that continue elsewhere. This is where multiverse ideas enter. They do not arise because astronomers find a literal hole in the sky leading outward. They arise as possible consequences of certain theoretical frameworks, especially some versions of inflation that suggest expansion may not end everywhere at once. In such pictures, one observable universe can be only one region within a larger inflationary setting. But this move takes cosmology away from established observation and into model-dependent extrapolation. The multiverse therefore occupies a very different scientific status from the observable universe. The cosmic microwave background, or cosmic expansion itself. Expansion is observed. Redshift is observed. The early hot universe is inferred from multiple lines of evidence tightly tied to measurement. The multiverse is not established in that same way. It is a possibility entertained because some mathematically serious models permit it, and because some versions of inflation naturally encourage the thought that our visible cosmos may be one bubble or patch among many. APS sources discussing eternal inflation describe searches for possible observational traces such as bubble collisions. But these remain attempts to test a speculative extension rather than confirmations of a settled fact. The difference matters deeply. Science does not place all ideas on one level merely because they are discussed in the same field. Some ideas are measured consequences. Others are theoretical continuations whose evidence remains indirect or absent. This is why the phrase "what is really there" needs unusual care at the final edge of cosmology. If it means what lies beyond the observable horizon, the most disciplined answer is probably more universe, though presently unobserved. If it means what lies outside the universe itself, the standard answer is that the question may not be well posed within ordinary cosmological language, because the universe already includes the space-time framework in which such an outside would need to be defined. If it means whether there are other cosmic domains not causally connected to ours, the answer changes again. Then science can say only that some theories allow such possibilities, that researchers have explored ways they might leave observable traces, and that no accepted direct evidence presently requires belief in them. The farther the question moves from horizon to outside, the thinner the evidence becomes. There is a quiet discipline in stopping there. Cosmology has great reach, but it also has boundaries. It can describe the expansion history of the observable universe, infer the hot, dense early state, measure the relic light of the microwave background, and map the later growth of structure with extraordinary precision. Yet precision does not remove every limit. Issei material has long emphasized that humanity may never know with certainty whether the universe as a whole is finite or infinite. That caution applies even more strongly to claims about an outside or a full multiverse. Science does not become weaker by admitting such limits. It becomes more exact. It marks the line between what is strongly supported, what is plausible extension, and what remains open speculation. The final unsettling truth is therefore not that a wall waits somewhere beyond the last galaxy, nor that a hidden realm has been discovered beyond the universe. It is that the deepest questions change their form as understanding improves. The old imagined edge dissolves into horizons of observation. Those horizons dissolve into geometry, topology, and early cosmic physics. Then even the hope of an outside begins to thin, because the framework of the question belongs to ordinary objects in ordinary space, while the universe in cosmology is the totality of that very space. A person seeking a border expects a line. Cosmology offers instead a sequence of limits of meaning. First a visual limit, then a causal limit, then a theoretical limit. At the deepest point, the universe may not have an outside in the ordinary directional sense at all. Still, the absence of a simple outside does not empty the universe of wonder. It deepens it. A wall would simplify the cosmos into a contained object, an undefined outside, or a reality whose larger structure may remain forever beyond direct test, leaves existence more open and more difficult to finish in thought. Even the most speculative ideas, when treated carefully, reveal something important. They show how far explanatory reason tries to go once the visible universe no longer feels sufficient as a complete frame. But careful treatment also prevents imagination from becoming evidence. The multiverse may be discussed, it may be modelled, it may motivate observational searches for subtle signatures. Yet until such signatures are found and accepted, it remains a possibility, not a measured component of the established cosmic picture. So this final region of the subject ends not at a discovered beyond, but at the limit of what present cosmology can responsibly say. Beyond the edge of the observable universe, there is most likely more universe. Beyond the universe itself, the meaning of beyond may dissolve because space and time are already part of what the universe is. Beyond that, theories such as eternal inflation may suggest wider realities, but those suggestions remain speculative without direct confirmation. The calmest answer is therefore the most exact one. Science does not find a physical wall at the edge, it finds horizons, continuations, and then a point where language itself must become careful. What is really there is, first, more than sight can reach, and then perhaps more than present evidence can securely name. The night sky remains unchanged in outward appearance. It still offers points of light against darkness, and the old instinct to search for a final border still rises easily in the mind. But after a slower passage inward, the edge no longer looks like a wall waiting in the distance. It becomes something quieter and more difficult. First it is the fading of light, then it is the boundary of the observable universe, drawn by travel time and the age of the cosmos. Deeper still, it becomes the ancient veil of the cosmic microwave background, beyond which ordinary light cannot yet carry direct sight. Deeper still, it becomes the hot opaque plasma of the early universe, the tiny first irregularities from which later structure grows, and the early expansion that helps explain why the visible cosmos appears so smooth and so nearly flat. At last, even the hope of an outside softens, because the universe in modern cosmology is not a thing placed inside a larger ordinary room. Space itself belongs to the story. What lies beyond the visible horizon is most likely more universe, still hidden by the limit of present contact. What lies beyond the universe as a whole may not be a place that present language can cleanly describe at all. The final image is therefore not a border but a sequence of horizons, each one replacing a simpler picture with a calmer and wider one. The universe does not end in a visible seam. It opens into deeper limits of observation, deeper layers of early history, and deeper caution about what can truly be known in that stillness. The old edge dissolves, and what remains is a cosmos that keeps its greatest distances not behind a wall, but within the quiet discipline of light, time, and understanding.